Okay, hello everybody. So this week we're going to be doing our recitation on chapter 4, and we will be studying each of Newton's 3 laws as listed here. So first we're going to talk about the first law, where a body acted on by no net force moves with constant velocity and zero acceleration. So I want to clear up a couple things about this. So usually when we're talking about projectile motion, it'll have a constant velocity in the x direction. And so you can say that for one of these problems, you can denote this as a sum of fx is equal to 0, and therefore that's why it moves with a constant velocity in the x direction. But in the y direction, gravity always applies. So in that case, there is going to be a force acting upon that object, and it's going to start decelerating as it goes up and accelerating when it goes down. Next, let's move on to number 2. F net is equal to ma. So the sum of all forces is going to equal mass times acceleration. If a net external force acts upon the body, then the body accelerates. And then number 3, we have every action has an equal and opposite reaction. This is just talking about action and reaction pairs. So if you were to say kick a soccer ball, right? You're gonna exert a force on that ball that is going to send it into motion. At the same time, the ball is also going to apply a force to you. So this is why it's relatively painless when you kick a soccer ball, but relatively painful if you were to kick a bowling ball, because the bowling ball has more mass. It's going to take a greater force to move, and therefore it's going to hurt when you kick it. Okay, so next up, I want to talk about just forces in general. Forces are vectors, and so they act like vectors, similar to position vectors. If you have components of forces that align in the x and y directions, then in order to superposition those two forces, you have to use Pythagorean theorem in order to do so. They also break down, like we did with position vectors and velocity vectors in the past. They also break down using trigonomic functions, and that's why I try to preach as heavy as I do on using those trigonomic functions so that everybody knows how to use them. So for a force, we have a box here, and we're pulling on it in this direction. So this is us here, and this is us pulling it. And we exert a force in this direction here, F. And so this force will eventually break down into two other force vectors, F of y and F of x. And so now in order to break this down, we have to take this angle here, and then we have to say that Fy is the opposite, so we're going to use sine, is going to be equal to F of cosine, or F of sine theta, excuse me. And then the same thing goes for F of x. Now, another thing that we also have to talk about is, so since this box has some mass m, gravity is pulling on it, and gravity is an acceleration. Mass times acceleration is going to give you a force. So there is going to be a force pulling downwards on this. Well, why doesn't the box just fall through the floor if there's a force being applied to it? It's because the ground itself applies a normal force that keeps the box stationary. And so we denote normal forces as Fn. And so we're going to have to also get into talking about frictional forces, which usually are drawn in the opposite direction of which the original force is being placed or being applied to. And so we'll call this F. And depending on whether or not it's a static or kinetic friction, we'll denote that as FS or FK. So FK for kinetic and FS for static friction. And we'll go into detail about that in a little bit. But stuff that you need to know for your test, we're going to be talking about how Fk is going to be equal to mu k times Fn. And so we usually denote our force due to gravity as weight, and that'll just be denoted by mg. So we can do a couple things with this now. We can try to find out how far are we pulling this box, or like what's the velocity after a certain distance. We're also going to assume that this force is going to be constant. So we're going to be constantly pulling at the same magnitude. So one thing that you guys are going to have to know is that when you're talking about these forces here, Fy is going to cancel with some of this weight here, and so then the normal force is going to be less. So Fn in this case now is going to be equal to, we're going to have Fy, or how about with this? Let's do this. We'll have mg minus Fy. And then the force that we apply to it to make it move in the x direction is going to be Fx net is going to be equal to f of x minus Fk. We're going to assume that the object is already in motion, and we're not going to talk about static friction at first. We're going to assume that f of x is great enough to break static friction, and we're just going to talk about f of k here. Okay, so we have a lot of the stuff that we already need. We can rewrite this as this is mg minus f sine theta, and this is going to be f, oh, I have made an oopsie. This should be cosine theta. Okay, and then this is going to be minus, because they're pulling in opposite directions. We'll assume that this is the positive x-axis. And so then this frictional force is denoted here. So Fk is going to be equal to mu of k times Fn. Well, we already determined that Fn is equal to mg minus f sine theta. And so then we can write that here. And so this will then be mu of k mg minus f sine theta. And so now we can go into different detail about, say, pulling objects up slopes and how that affects this as well. But I think that those are topics more readily covered by energy, so we'll do those in future classes. So again, Fx net is going to be equal to f cosine theta minus mu of k times mg minus f sine theta. Okay, so next up I really want to talk about the superposition of forces. So say we have an xy axis here, and we have one force pulling this way and one force pulling that way. And so we can denote this as F1, and we can denote this one as F2. So then what we can do in order to superposition these is we just have to add them. So we have F1 plus F2. So what's going to end up happening here is, let's see, well, let's break them down into their components. We have Fy and Fx, and we're going to change the notation here so that this is 1, and we'll do the same thing for the other side. This will be Fy, and this will be 2, and this will be Fx, and this will be 2. So then this breaks down further into, we'll say that this is Fnet here. So then we'll say that this is equal to let's do Fx first. Fx1 plus Fx2 plus Fy1 plus Fy2. And so once we add these up, we can also denote the direction here. So this will be I hat and J hat. So then real quick we can say that Fy1 is going to be equal to F1, and so this is our theta. We're going to take this angle to be phi here. I'll write that again. So we can do this as F1. This is opposite, so this is sine of theta. And then Fx1 is going to be F1 cosine of theta. And then we can do the same thing for the other side. Fy2 equals F2 sine theta, or sine phi, because we changed the angle. And then Fx2 is going to be equal to F2 cosine of phi. And so then we can just start plugging in all of this. So then we have F1 cosine theta plus F2 cosine phi, I hat plus F1 sine theta plus F2 sine of phi. And this is J hat at the end here. Okay, so once we've added up all these components, the only way to actually find Fnet outside of component form is to use Pythagorean theorem. And so then we can do that, and we can say that Fnet is going to be equal to the square of our x component plus the square of our y component. So F1 cosine theta plus F2 cosine phi squared plus F1 sine theta plus F2 sine of phi. And both those quantities are squared. And so once you plug in all your numbers, this will give you the magnitude of your force. And then if we want to find the direction, or the new direction in which this points, we just have to take our inverse tangent function. So we'll say that this is, we'll call this some angle, I don't know. We can just say, what should we use for this? I don't know, theta prime. And then we have to use the y component over the x component like we did before. And there you have it. That will yield your angle. So we've done a lot of the mathematics here before. So we haven't really run into anything new. We're just using it in a different way. Next up, I just want to talk about briefly the units of force. So the unit that we use for force is going to be the Newton. And 1 Newton is going to be the force it takes to accelerate 1 kilogram object at 1 meter per second squared. Okay, so we're exploring this problem where we have a spaceship, right? And we have an astronaut floating outside his spaceship. He wants to get back to his spaceship, but he only has a wrench on him. He can't lose his spacesuit because he would perish in space. So using Newton's third law, we can say that the force applied that the astronaut applies to the wrench is going to be the negative of the force that is applied to the astronaut. So this is going to be our FWR, and this is going to be our F of our astronaut. These are going to be equal, but so they're not drawn to scale, but the acceleration of the astronaut is going to be far less, because when we start substituting in here our equations for force, we can see that the mass of the astronaut is going to be far heavier or far larger than the force of the force on the astronaut, if that makes sense. So this is going to be MA. So since the wrench has less mass than the astronaut will move slower than what he threw the wrench, and the ratio and the acceleration of the astronaut is going to be equal to the acceleration of the wrench times the ratio between the wrench and the mass of the wrench and the mass of the astronaut. Okay, so now I'm going to start going over some of the homework. If I can find my pen, there it is. Okay, so we have a car that is deep in the mud, and we want to attach a rope to a tree to pull it out. So in order to do this, we have our car here, right? I'm just drawing it. Here's the wheels. And we've got our tree over here. And we have a rope tied around the tree here. And so what we want to do is we're trying to get this car out of the mud. So first we have to have this tension force here, which is going to be applied in the direction of the rope, and we have angles theta here and theta here, and we have this F here pointing in that direction. So we can take the sine of theta here to be equal to F over T, or F1 over T. This gives us that F1 is equal to T sine theta, and F2 is also going to be T sine theta. And so all we have to do is we have to say that, so this is also F2. So I'm just putting a comma there to represent that. So all we need to do is we need to say that F is equal to F1 plus F2, and that'll give you 2T sine of theta. Okay, so now in real life, we know that ropes stretch. So we want to know what happens if, or what force would be exerted on the car if the angle increases to a new angle and you still apply the force found in part A to its center. So from here, all we have to do is we have to swap around t sine theta. So now we have t is equal to f over sine theta from before. But remember that there's two different forces here, so we add a 2 here, just like we did in the first one. And so then, but f from the first problem is here, so all we have to do is we'll take 2t sine theta, and this is our new sine theta, so this is going to be theta prime. And so then the 2's cancel out, and then you just have t times the ratio in between sine and sine theta prime. Okay, so next up we have this ceiling here, and we have a mass that is dangling by 2 ropes, with this angle here is going to be alpha, and this angle here is going to be beta. And so what we have to do, we're given values for m, alpha, and beta, and we have to first pick the free body diagram, and then we have to sum the forces, and we have to use the terms here. So as this is asking for just a, they're just asking for an algebraic answer and not a numerical one. I'm just gonna say that we have that W here is equal to mg, and so then mg is going to be distributed, or W is going to be distributed between these two. Also want to note that this is a dotted line, and so is this one, just so you know exactly which way the ropes are going to be getting pulled from. And so this free body diagram is going to be pretty easy. You always have mg at the bottom, and then you just have to pick which one of these ropes accurately describes or which free body diagram actually describes this physical situation here. So I'm going to be skipping this one because it's just asking for the algebraic answer. Next up, we have a question that seems to be part of a lab. So what we have is we have a mass here, right? And it asks for how big is the normal force acting on the block due to the ramp. And so we know that mg is always going to point downwards, but we want the normal force here, which is pointing in this direction. So we have to break up this force here into its composite of its forces here. So this angle here is going to be theta, which is going to be the same as this theta, as they're going to be similar triangles. So now in this case we can say that, so this is W, and this is our hypotenuse, this is going to be our A, this is going to be our O. So this O force is going to be also pointing in that direction there, and A is going to be the opposite of the normal force. So now we can say that we have sine of theta, and our hypotenuse is going to be W, and this is going to be over A. It's going to be over O, and then cosine of theta is going to be A over W, and this is what we're looking for here. So then we can just say that A is equal to W cosine theta. And so then Fn is equal to W cosine of theta. Okay, so next up we have a battleship here, and inside the battleship it has some sort of artillery cannon. And so we have this artillery cannon and the projectile itself is going to have some mass m, and it's going to be accelerated out of the gun. It's going to experience some sort of acceleration. So this is just a basic Fnet problem. So all you have to say is Fnet is equal to ma, and so then the force is just going to be the mass of the shell times the acceleration it experiences inside the barrel of the cannon. And so you just need to plug in algebraically what this is going to be. And then part B asks for the magnitude. So it's not asking for a direction, so you don't have to include any negative sign, but then you just use Newton's third law, and it's still the same thing, but you just put some absolute value signs on this, because the shell is going to exert the same amount of force on the boat as the boat is, so it's just going to be Newton's third law. So the shell is going to exert an equal and opposite force on the boat. Okay, so the next problem is one that we kind of already touched on in the review of the chapter kind of deal. So we have some mass here that experiences two different forces. This is going to be F1, and this will be theta 1, and this will be theta 2. We use theta and phi. So go back to the earlier part of the video, and you can sum up you can break down these forces into their x and y components, and then sum them up, and from there you can write out expressions for the x component of the force, the y component of the force, and then you can find the angle, just like we did before. And yeah, this one's we've already done this one, so go back and watch that part of the video first. Okay, so next up we have a box that has a force here and a force here on it, and in this problem they first want you to draw a free body diagram, so you just have to include this force, gravity, and the normal force. So then it wants you to find the x component. So for this one, there's not going to be any x component here, because it's only going to be pointing in the, or it's not going to have a y component. It's only going to be in the negative x direction. This one is going to have one in the positive x direction and one in the negative y direction. So, and this surface is assumed to be frictionless. So mu of k dash s equals 0. So we don't have to worry about friction at this point. So now f of x is going to be equal to negative, which one is this? This is negative f1, or the magnitude of f1. And then it's going to be plus, and this is going to be, we can draw a little triangle here. So this is going to be f2, f1, and so then this is going to be the opposite, so that's going to be the sine, so we're going to use the cosine, so it's going to be f2 cosine of theta. And so then fy is just going to be equal to 0 from f1, so we can put that there, and then we're going to have negative f2 sine of theta. And then you should also, if it's asking for the net force, you have to add on mg. So then this is just going to be plus mg here. And the negative is concealed in the g component. And it's also, and if it's asking for fn, then it's going to be the negative of this, because you just have to flip it, because it's what pushes back up, and since it's pushing up, then it's going to be positive. And so now we have to find the block's acceleration. So all we have to do is say that a is equal to f over m. And so then that's just going to be the fx component. So you just plug this in here. Next up, we have two people hanging on a rope here. And so I'll just draw them as point masses. So one hangs here and one hangs here. So then we have M1 and M2. And so the tension in the rope, since it's not breaking, has to be T is equal to W1 plus W2, where W1 is going to be the weight due to this one, and W2 is going to be the weight due to that one. And so then we can factor out a g in these, and so then we have M1 plus M2 times g. And so then we just need to add their masses up and then multiply by 9.81, and that will give you the tension in the rope. And so now it's going to ask for the tension in the rope in between M1 and M2. And so now all you have to do is you only have to take one of their masses. So this is just going to be that T is equal to, I believe this is W2, which is going to be M2 times G, which should then give you the tension of the rope there. Okay, so next up we have two masses, and they're going to be attached via a pulley, and one mass is going to sit on a table here. So this is going to be M1, and this is going to be M2. And so what we have to do is we have to draw some free body diagrams. So you just have to include T, N, and W for this one, and then there's going to be a T going this way and a W going that way for the next one. And so now the problem is going to ask for the acceleration a2 that the block of mass m2 experiences in the y direction. And so we know a couple things, that we know that F net in the y direction is going to be equal to T minus is going to be equal to W2 here. This is W1, W2. And so then W2 is just going to be M2 times G. And then we know that F equals MA, and then we can substitute in the stuff here for this part. So MA is going to be equal to T minus W2. And so then we just need to solve this for A. So this is A2 is equal to T minus W2 all over M2. So next up, we know that that A1 is just going to be equal to T over M1, and so it's And so all we really need to do here is this is going to be end up being a ratio of the two masses. So we know that we have a t in here, and then t is equal to this stuff here. So then what we can do is we can start substituting in stuff. Okay, so here we can say that a2 is just going to be negative of a1. So we can plug in a1 here and have that be negative. And then we can say that t is going to be equal, or we have that a1 here is going to be equal to t over m1, which then we can say that t is equal to m1 a1. So we can substitute in that here. So we have m1 a1 minus m2 g all over m2. And so then we can solve this for a1. We just need to get both of the a1s to the one side. So then we can say that this is equal to negative m2 a1 minus m1 a1 is going to equal m2 g. We can divide this entire thing by -1, so we can remove the negative signs. And then we can factor out an a here, and then we have m2 plus m1 equals m2g. So then we can say that a1 is going to be equal to m2g all over m2 plus m1. And now, since we have the value for m1, and we have an equation here for t, we can say that t is just equal to m1 times m2g all over m2 plus m1. And then you just have to plug in your values from there.